Welcome everyone, and thanks so much for tuning in. If you cannot see the screen, please enter that comment in the questions box in your GoToWebinar panel on the right-hand side of your screen. We're pleased to have you join us for today's Southeast Coastal Ocean and Coastal Acidification Network State of the Science webinar series, and the title of today's presentation is Potential Effects of Climate Change on the Ecotoxicology of Pesticides and Contaminants of Emerging Concern, Implications for Ocean Acidification Interactions. This series is hosted by the Southeast Ocean and Coastal Acidification Network, or SOCAN, and this series lays a foundation for the state of ocean acidification science in the Southeast region. And these webinars are intended to create a dialogue among scientists to identify what we know, what we don't know, and what research in other regions of the United States can be applied to help us better understand ocean acidification and its impacts in this area. And with this awareness and research access and its implications, webinar participants will be able to collaborate to better understand and adapt ocean acidification as we move forward. I'm Paula Keener, and I am with the NOAA Office of Ocean Exploration and Research, and I'm a member of the SOCAN Steering Committee, and I'll be moderating today's session on behalf of the committee. Jen Bennett-Mintz is Education and Outreach Coordinator for NOAA's Ocean Acidification Program, and she's on the line with us, and she'll be helping to facilitate today's session. During the presentation, you will all be in listen-only mode, and you're welcome to type your questions related to technical issues or for our presenter into the questions box in the GoToWebinar panel on the right-hand side of your screen. We'll be monitoring these incoming questions and will respond to them or post them to our speaker. And we are also recording this session, and the video recording and a PDF of the presentation will be available on the SOCAN website. We are very excited to welcome Dr. Geoff Scott with us today. Geoff is a clinical professor and chair of the Department of Environmental Health Scientist at the Arnold School of Public Health at the University of South Carolina. His research experience is vast and includes serving as an aquatic toxicologist for the United States Environmental Protection Agency, studying the impacts of water chlorination on estuarine organisms, and conducting ecological assessments of oil spills around the world. Geoff has also conducted research on hazardous waste sites, and he has also assessed the impacts of agricultural pesticides, synthetic fuels, and urban non-point source runoff on coastal ecosystems. Geoff has also worked with NOAA's National Ocean Service, National Centers for Coastal Ocean Science, the Center for Coastal Environmental Health and Biomolecular Research, or CEBR, from 1990 to 2014, conducting research that measured the health of coastal ecosystems and evaluated the impacts of changing landscape ecology from urbanization on ecosystem and human health. Geoff was director of NOAA's CEBR Center from 2001 to 2014, and he formerly was the acting director for NOAA's Center for Human Health Risk at the Hollings Marine Laboratory from 2009 to 2011. So Geoff, welcome. We're pleased to have you with us, and I'm going to turn the presentation over to you now.
Thank you so much, Paula, for that tremendous introduction, and really appreciate that. And it's so good to be with so many people this holiday week of Thanksgiving. The topic I want to talk to you about today is sort of near and dear to my heart, and really wanted to talk specifically about the potential implications of climate change on a part of ecotoxicology we don't often think about, and that is how climate change affects water quality and how that in turn affects the toxicity of many of these contaminants. So we'll jump right into this. Let's see here. Let me go to my next slide. Here we go. All right. So first of all, I have a lot of folks to thank for this, and particularly my colleagues at the Center for Coastal Environmental Health and Biomolecular Research, Dr. Mike Fulton, Marie DiLorenzo, Paul Pennington, Ed Worth, Pete Key, and Jan Moore. Also my colleagues Tom Chandler, Sean Norman, and Dwayne Porter here at USC, Dr. Terry Beidelman at Environmental Canada, and also I'll be presenting some data presented to an EPA panel by Dr. Tom Peterson at the National Climate Data Center. So I'll jump right into the first slide, which is a slide many of you I'm sure have seen different versions of, but we see in red the atmospheric increase in carbon dioxide that has been attributed to the combustion of fossil fuels and other sources of carbon dioxide that essentially have risen in the past 40 or 50 years to dramatic levels. We see in blue the concentration of the CO2 as well in seawater. And then we see in that light blue the effect of sequestering that CO2 in seawater, how it lowers the pH in seawater, leading to potential concerns about ocean acidification, which is what SOCON is all about, specifically here in the southeast U.S. So just a couple of facts about climate change. Presently, the levels of carbon dioxide are at or about 400 parts per million. That's about a 25% increase since the start of the Industrial Revolution and about a 12% increase since 1960. Most scientists attribute this increase to having caused about a 1 degree Fahrenheit increase in mean global temperatures during the 20th century. And of course, the projections for the next half of this century, or the first half of this century, are that we will see elevated temperatures of somewhere between 1.5 and 4.5 degrees Fahrenheit, depending upon what actions we take to reduce some of these CO2 emissions. Now, if we look at the greenhouse gases, we have carbon dioxide, which is the major contributor at about 400 parts per million. About 55% of the greenhouse gases are CO2. Next are the chlorofluorocarbons, which contribute about 24%. However, one thing about the CFCs is for one molecule of CFC will have 12,000 times more potential to absorb infrared radiation than one molecule of CO2. And the biggest concern is these are increasing at a rate of about 5% per year, which means in 20 years we're going to double the concentrations. And of course that's even going to be exacerbated as things get warmer due to climate change. Then we have methane, which can be from natural as well as man-made sources, contributing about 15% at about 2 parts per million in the atmosphere. And again, methane is 20 times more potent than CO2 at absorbing infrared radiation and is increasing at about 1% a year. And then we have nitric oxide, which is a byproduct of combustion of petroleum, particularly in automobiles, which is about a 6% contributor, and it's in the parts per billion range and increasing at about 0.25% per year. Now, if you want to read up on any of this, and I'm sure many of you that are interested in climate change are well aware of this, but I'll just point out that we have the 2009 and 2014 Interglobal Panel on Climate Change reports, and they're available online, and they're a wealth of information, all peer-reviewed, and provide the latest and greatest information that you may want to consult. Now, this next slide is taken from some of the data in the 2009 report, and this was information presented by Dr. Tom Peterson to an EPA panel on pesticides looking at the effects of climate change on pesticides. And so what we see here, if we start with that 4-panel box, you'll notice there's a little orange window that's right in here. And if we blow that little window up, as you can see in here, what we see are 4 different scenario models: a high emission scenario, an even higher emission scenario, a lower emission scenario, and then stabilization at 450 parts per million. Those are different scenarios posed in the 2009 report. One of the first things Dr. Peterson liked to point out at that panel was that the current models all underestimate the actual concentrations that we see in the environment from observations, and that the models are highly conservative. And so I think that's the one point he made to us in his presentation. The other 2 points is the longevity of carbon dioxide in the atmosphere, the half-life. 100 years from now, 1/3 of the CO2 emitted today will still be there, and 1,000 years from now, 20% will still be available in the atmosphere. So the persistence is tremendous, and we have to be very concerned about that, because the actions we don't take today will be left with the consequences of that for the next several hundred years. So how does climate change affect the oceans? What are some of the threats? Well, climate change may directly affect the growth, survival, persistence, distribution, transmission, and virulence of disease-causing organisms and harmful algal blooms, and it may affect the distribution and concentrations of chemical contaminants in coastal and ocean waters. And that's really what I want to talk about today. Major climate factors are temperature, precipitation, and that's associated with drought, flooding, and runoff, sea level rise, salinity extremes, extreme weather events, and ecological shifts. And today we'll also be talking a little bit about changes in oxygen levels, hypoxia, and also pH. So one of the first things I want to talk about is the effect of increasing temperature. And one of the things that increasing temperature will do is to melt polar ice, and this will increase the release of many of these chemicals that have been sequestered in the ice in the Arctic regions and Antarctic regions as a result of the Industrial Revolution. Here's another slide from Dr. Peterson that was presented to the panel, and these are the current projections in temperature change, and we'll start over here with the present day change from 1993 to 2007. Here's your scale. These are in degrees Fahrenheit. So as you can see, for most of the U.S., we're looking at a 1 to 2 Fahrenheit change in temperature. The projections from 2011 to 2029 are for even more extreme change, and particularly in the Arctic regions. As you can see, temperatures of 4 to 5, even 6 degrees Fahrenheit are projected. And then we have the high and low emission scenarios for the mid-century and into the century, and I don't want to go and talk a whole lot about that. Obviously, you can see the profound change up all the way up to above 10 degrees Fahrenheit that would be projected. Now, one of the ways to sort of describe how climate will change as a result of these models is the concept of moving states. So the climate, let's just, oops, let me go back, sorry. So if we go and take a look at the climate in Chicago, which just had a foot of snow the other day, by the middle of the century, it's going to look at like the climate in northern Mississippi or Louisiana and under the low emission scenario, and then it will be very close to what we see in New Orleans by the end of the century. And under the high scenario, it will be the same climate as we see in Dallas, Texas. If we take a look in the New England area, we can see under the high scenario, the New England environment will be like that of Raleigh. So this sort of gives you a way to at least get your arms around what magnitude change we'll see in these areas. If you go all the way through the global climate change reports, the things that you come away with from all these detailed tables that you'll see is overall we're going to see more extreme weather, more increased temperature extremes, warmer nights, fewer colder nights, increased heat waves, increased heavy precipitation events, increased periods of drought, increased tropical cyclone activity, and increased sea level rise. Now, this next slide is a slide of looking at global changes in surface temperatures of the oceans from 1970 to 2004. And if you look in the middle of the slide here, this scale is in degrees centigrade change, and the pink and reds are anywhere from 2 to 3.5 degrees centigrade change in that 34-year record. And you'll notice as we go to the extreme areas in Alaska and in northern Canada, we can see that you don't get equal warming everywhere on the planet. It's more extreme in the polar regions. And this is of grave concern in terms of what may happen to the ice up in these regions. According to Terry Beitelman and the folks at Environmental Canada that helped conduct the Arctic Climate Impact Assessment, the Arctic region is likely to warm 7 to 13 degrees Fahrenheit during this same time period of this century. And in fact, the average temperature in Antarctica over the past 30 years has essentially gone up by 6 degrees centigrade the past 30 years. And that has resulted in the melting of glaciers and major loss of the ice in that part of the world. Right now, we estimate that more than 279 species of plants and animals are responding to climate change by moving closer to the poles. And of course, the loss of ice will have profound impacts on some pretty important charismatic macrofauna like polar bears, Adele penguins, and the walruses that we see here in this slide. Well, if we actually take a look at the ice that's melting and take a look at some of the chemical contaminants that have been sequestered in that ice from the Industrial Revolution, you can see, and these are in concentrations in parts per trillion, that the ice contains anywhere from 105 to 214 parts per trillion lead, 1.3 to 8.1 parts per trillion mercury, 3.4 to 36 parts per trillion cadmium. Now, if we take a look at some of the organic pollutants, we see some very interesting things. And one of the most interesting things is the level of a pesticide called endosulfan. If you were actually to go to one of those polar bears and take a sample, the two most frequent organic chemicals you would find in that polar bear would be endosulfan and DDT. And in fact, endosulfan is a pesticide used on tomato crops to kill stink bugs, but it has a very high Henry law constant, and because of that, it tends to be transported to the globe, to the polar regions. The levels we see here range from 30 to 360 parts per trillion, which appear pretty low. However, the marine water quality criteria is 8 parts per trillion. So this is at a minimum 4 times above the salt water criteria for this particular contaminant. If we take a look at the chloropyrifos, an organophosphate insecticide, it occurs at about 16 parts per trillion in ice, and again the water quality criteria for that is 6 parts per trillion, a little over 6. So both of these chemicals are being phased out by EPA now, but unfortunately what is in the ice is remaining there and will be released. So this has grave concerns. We also see herbicides like atrazine and also up to 18 parts per trillion DDT melting in these areas. If we look at the West Antarctica ice sheet, it's losing about 210 tons of ice per year, which is around 1 to 4 kilograms of DDT being released into that part of Antarctica each year into these global systems. Now, the next point I want to make is increased thermal stress. One of the things that we see in this next slide, you'll notice we're taking these two pesticides I just mentioned, endosulfan and chloropyrifos, and we're looking at the effect of low-level exposure of these two pesticides to 4 different species of freshwater fish in terms of their upper thermal tolerance. Let's just use the rainbow trout, for example. Without any pesticide exposure, their upper thermal tolerance is from 24.8 to 30 degrees centigrade. However, if we expose them to these two pesticides, we lower their upper thermal tolerance somewhere between 5 and nearly 6 degrees centigrade, which essentially means they will not be able to survive temperatures below 20 degrees centigrade. And that is a very important finding, because what that means, at the very time we are turning up global temperatures, we're turning down the thermostats of the animals that have to respond to that, which means they're going to be much more sensitive to this effect. Now, if we take a look how frequently the pesticides and things like that occur throughout the environment, well, this is a national survey done by the U.S. Geological Survey, and you'll notice for 3 major classes of chemicals, insecticides, antibiotics, and flame retardants, they occur at around 45 to 60% of all sites in their national survey. And if we look a little closer to home, these are levels of perfluorinated flame retardants in dolphins in Charleston Harbor. And you'll notice they're higher than anywhere else in the world. And in fact, the levels in the blood of the dolphins rival the levels, the mean concentrations we actually see in workers that produce this particular class of chemical. Similarly, if we look at an antibiotic like oxytetracycline, this is looking at a barrier island in South Carolina. These are levels in the water treatment plant of this particular antibiotic, which is then land applied onto golf courses at this resort. And as you can see, we find tetracycline finding its way onto the golf course, to the water hazards, and then all the way out to the receiving streams. The thing that's of concern here is these low levels of antibiotics are not sufficient to kill bacteria, but what they do allow is to breed antibiotic resistance. And then, of course, we have to be concerned about the pesticides. And this is a recent survey done by the U.S. Geological Survey nationwide, looking at the levels of frequency of detection of some major classes of herbicides and insecticides over two different 10-year windows. 2002 to 2011 are the most recent. The light green, light purple, the dark green, dark purple were the 92 to 2001 time period. And what we generally see for most of these pesticides is only slight increases of some chemicals, but by and large either equivalent or very similar levels of occurrence. However, there are some very interesting findings from this report by Stone et al. 2014. And in terms of health effects, during the most recent survey, only one stream in the survey actually exceeded public health or human health benchmarks of adverse effects, compared to 17% of the agricultural land use and one mixed land use stream that exceeded those human health benchmarks in the earlier 10-year window. So clearly the pesticide risk to humans has gone down dramatically during this most recent 10-year period. However, there are some very big concerns here in terms of effects on aquatic life benchmarks. In the most recent survey through 2011, 2/3 of the agricultural streams, and more importantly, nearly 90% of the urban streams exceeded these chronic aquatic life benchmarks. And some of the chemicals involved are things like fipronil, malathion, permethrin, some of your pyrethroids, and new generation contemporary use pesticides. In fact, a panel in California that I'm on, trying to come up with a new list of emerging contaminants to monitor. We have 3 contemporary use pesticides, bifenthrin, permethrin, and chlorpyrifos, which fall out in terms of the pesticides we should be monitoring. And you'll notice these are very similar to what we see in stone for the pyrethrins and also the chlorpyrifos that we saw earlier excuse me, in the Arctic region. You'll also notice we have 2 classes of flame retardants, which we showed you earlier, and then also triclosan, which is an antiseptic solution, which is very similar to the issue with the antibiotics. Now, in addition to the effects of temperature and melting ice and release of these contaminants, we also have to be very concerned about sea level rise along our coastal areas. So when we really begin to talk about how climate change will affect estuaries, we clearly know that temperatures are expected to rise. Sea level is expected to rise, which may increase salinity. And we'll talk later about changes in precipitation rates, which may also affect salinity, maybe in a downwards in terms of lower salinities. So really, one of the things I want to talk about is how do these extremes change some of the toxicological assessments we currently do. And this really goes back to some of the work done by the scientists there at CBER, Marie DiLorenzo, Mike and Pete and Ed Worth and Paul Pennington, Jan Moore. Under normal bioassay procedures, we run this test at 25 degrees centigrade, a mid-range of salinity, about 20 parts per thousand, around a pH of 8, and at or above 60% oxygen saturation. To simulate climate change stress, we raise the temperature up to 35 degrees C, the salinity up to 30 parts per thousand, the pH we lowered to 7, and then we dropped the oxygen level to 20% oxygen saturation. And so what we really wanted to do is compare how phytoplankton, shrimp, and clams responded to those conditions. So we'll first talk about the chemicals that were tested by the folks there at NOAA. They looked at phytoplankton, looking at Dunaliella, Tortolia electa, that were exposed to 3 different herbicides, atrazine, diuron, and amitrin, and then ergorol, which is a copper-based chemical. And then we also looked at chlorothalonil in grass shrimp and carbamyl, a herbicide, and a fungicide and a carbamate insecticide, and resmethrin, which is a pyrethroid. And then we also looked at resmethrin in the juvenile clams, so grass shrimp, Paleomenides pugio, and Mercenaria for the juvenile clams. So let's take a look at some of the results. This is for the algae, for the phytoplankton. And what we see is a curve here, and let me sort of orient you here. The normal standard temperature and salinity at 20 degrees C, 20 parts per thousand salinity, and a pH of 8 is in black. And then we tested at high salinity, high temperature, and then the combination of high temperature and high salinity. And so what I will point you to is the 50th percentile. This is the LC50. You'll notice that the combination of these different variables lowers the LC50 by nearly 3 to 4-fold in making this more toxic. So our current estimate of pesticide toxicity using this species of algae is way underestimated under climate extremes. So most pesticides were more toxic under increased temperature and salinity. We see the multi-stressor effect of salinity and temperature pulling that curve to the far left, and changes in climate could really affect the sensitivity of phytoplankton to pesticide exposure to these types of chemicals. And so the toxicity curve is shifted to the left, indicating temperature and salinity really increased the toxicity. Similarly, if we look at grass shrimp, we see a similar effect. Here's your standard curve in black, high salinity. You'll notice no difference in just high salinity, but the combination of high temperature or high salinity and temperature once again shifts the LC50 from around 500 down to nearly 100. Again, about a 4-fold reduction in toxicity. In other words, this chemical is 5 times more toxic than it is under standard conditions. That was for chlorothalonil. However, not all chemicals responded the same way. If we look at the response to the pyrethroids, you'll actually see high salinity actually made the pesticide less toxic. Here's your standard temperature and salinity, and high temperature, or the combination of high salinity and temperature, did not dramatically affect the shape of the curve. So what we really see here then is it really will depend on the class of chemical, its mode of action, in terms of the response. Now, another factor to consider here is the fact that we have major changes in precipitation occurring under climate change. If we start with this box on the far right, these are the rates of increased heavy precipitation measured over time from 1958 to 2007. You'll notice in the northeast U.S. we have had a 67% increase in heavy precipitation events during that time period, a 20% increase in the southeast United States. And then under these different emission scenarios, we project even more dramatic changes in what we call heavy precipitation events. Now, this has a major and profound impact in coastal areas which are undergoing urbanization. Most of us know that with urbanization, over half the U.S. population lives in the coastal zone or Great Lakes. And in fact, over 25% of all land conversions to suburban urban areas occurred from 1982 to 1997 since the U.S. was settled. In fact, there are 5.19 times more commercial activity per land area and 5.38 times more people per land area in the coastal zone. And that more commercial activity means much more pollution in coastal areas. Of course, the bigger thing that happens in coastal areas is we have made major modifications in the landscape ecology to increase the imperviousness, which in turn increases the delivery of chemicals to watersheds. We've already seen in Stone and L's national survey the highest areas of greatest impact for pesticides are not ag areas, they're urban areas where there are high levels of imperviousness. So I'm going to skip that slide and just move right on to this next slide. And of course, where the greatest rate of urbanization is occurring is in the southeast United States, the area from Cape Hatteras, North Carolina to Cape Kennedy, Florida. And in fact, if we take a look at population growth trends, this is the red line, is the population curve for Horry County. And I'll point out that you have a population doubling time in this area. We go from 1970 to 1990, a doubling in about 20 years. Another interesting thing with this rate of rapid influx of people, we have the three fastest growing cities in the East Coast of the United States, Myrtle Beach, Charleston, and Hilton Head in South Carolina. And of course, the other distinction now Myrtle Beach has is the #1 city in the U.S. for violence, for violent crimes, which goes with that rapid growth, but that's a whole nother separate discussion. But one of the things that happens when you pave paradise and put up a parking lot as you urbanize areas, you really increase the urban footprint. And in fact, for every 1% increase in population growth, we typically see a 5% increase in urban footprint or impervious cover, which means more runoff. And this is just a time series for Charleston just to make that point. And in fact, if you have a population doubling time of 20 years, with those ratios, you're going to have an urban footprint doubling time of 5 years, which means you're really dramatically changing the landscape ecology. One of the problems is the way we build houses. Most subdivisions today are less than a quarter-acre lot size, and the numbers inside these different lot sizes are the percent imperviousness you get. So you can see with a typical 1/8 acre lot, you have 65% imperviousness because of the house itself, the sidewalks, driveways, and other things. Under normal natural conditions when it rains, about 10% of the rainfall runs off. But when we get to 10 to 20% imperviousness, we double that amount of runoff. 30 to 50% impervious, we have a 300% increase in runoff. And then 75 to 100% imperviousness, as we would see in an urban area, 500% increase in the runoff volume. And studies have shown when we get above 30% impervious cover, we begin to see degradation of ecosystem services, specifically the harvestability of shellfish and safe swimming in recreation for contact recreation. Now, this next series of slides talks a little bit about how rainfall can affect water quality conditions in estuaries. So we have a dry weather period. This is a hydrolab printout of salinity, water depth, dissolved oxygen, pH, and temperature for Wadmalaw Island down here in South Carolina. And then what we see is when we have a rain event, you can see a dramatic drop in salinity. And the other thing I'll point out is you'll notice the depths at low tide. You have nearly a half meter volume or a half meter depth where normally you do not have any volume. And that is all the fresh water running off during that event. And you can see how that lowers dissolved oxygen. It also lowers pH. And you can see under even normal conditions, we have low pHs at or right above 7, pH of 7. Now, if we start to look at sites with minimal imperviousness and rain, we don't see that dramatic of effect on salinity. You'll notice to the left, dissolved oxygen, pH, and temperature again. But you'll notice when we have more than 50% imperviousness, we get much greater swings in salinity, and we also see great reductions in dissolved oxygen to hypoxic conditions, and we can see dramatic drops in pH that oftentimes accompany these rain events. So one of the other things the folks at our SIBR lab in NOAA have looked at is the effect of hypoxia and pH. And so we're now looking at the effects on clams. And again, these are Mercenaria, juvenile Mercenaria clams. So here's your standard test at normal temperature, salinity, pH of 8, and dissolved, normal dissolved oxygen above 60% saturation. And then we see the effects of the combination of low pH and hypoxia, low pH and hypoxia. And what we see is the curve is shifted to the left. Again, just as we saw earlier, again, looking at the LC50, we've cut that in by almost, made it almost 2 times more toxic under these conditions, which means our current toxicity testing for pesticide registration is greatly underestimating the effects that may happen when we have these kind of conditions in our receiving streams. So this multi-stressor exposure of hypoxia and low pH is something that we have to pay a lot of attention to. The studies found that low pH did cause shell thinning in the clams, and that is a major cause for concern. We've all heard earlier seminars about the effects of pH on juvenile shellfish, and so we have to be very concerned about what this may hold in the future. So changes in climate could very well affect the sensitivity, particularly to marine bivalves with pesticide exposure. Another concern in terms of pesticide use is as we have crop production shift from the Midwest to the northern part of Minnesota and southern Canada because of the shifting temperatures, the breadbasket is going to shift, and the places where we currently grow a lot of our wheat and corn and other things in the Midwest will have 30 to 60% less rain and will not produce as many crops. Also, under higher CO2 conditions, you will see a decrease in the protein content of your P3 plants, like your food plants like soybeans. Your P4 plants or weeds actually thrive under high CO2 conditions, which means we're going to have to use more herbicides in order to control the weeds. Similarly, the insect pests, in order to meet their protein demands with plants that don't have as much protein, will try to consume more of the plants in order to meet those needs, which means we will likely have to use more insecticides. So in sort of summarizing what we just showed you with some of the urbanization effects, I want to make a couple of quick points to you. We clearly know there is a distinct correlation between population density and imperviousness. If we move to this graph, the more imperviousness we have, the higher flow conditions we have during runoff events, which means in turn we deliver more harmful things, bacteria and chemical contaminants, including pesticides and some of the other things we have seen. This is a slide from Ann Blair, and Ann, I see you're on the line, so glad you're watching, because I think Ann really summarized this in her really great paper looking at using curve numbers, soil curve numbers, to predict runoff potential for different soils in the southeast United States. So what she shows are curves with 1%, 31%, and 55% imperviousness. And this is the projected amount of runoff you would have in a rain event under those conditions. So you can see when we have 55% imperviousness, we're estimating about 42% runoff. And you can see with increasing precipitation with climate change, the amount of runoff is going to get even more dramatic. Of course, under drought, it's going to go the other direction. However, during drought, the other thing you have to keep in mind, if you're having dry deposition of chemical contaminants, in addition to the actual use of things like pesticides, your PAHs, for example, that will fall out of the atmosphere, your period of dry weather periods between rain will go up, and thus you're going to get more loadings of those contaminants, which will then in turn drive their concentrations up when it does rain. So these are some of the different things you will expect to see in urban runoff: phosphorus, nitrogen, copper, lead, and zinc. I particularly point those out. We just are in the process of completing a study with South Carolina Sea Grant, and we are seeing enriched levels of those three metals in addition to cadmium and chromium and arsenic in retention ponds well above sediment quality criteria. So we have to be very concerned about those metals. We also see increased levels of PAHs and fecal coliform or harmful bacteria in that runoff. This next slide is a slide by some folks at the Pacific Northwest Center for NOAA, the Fisheries Science Center in Seattle, a paper by Marquise et al. 2010 looking at climate change and seafood safety. They did a review of the literature and looked specifically at biotic responses to temperature salinity interactions with different classes of pollutants. So these are metals, and the scale is no change, a positive or less toxicity, or more toxicity, which would be negative. And so, for example, you can see with the metals, over 70% of the studies show increased salinity temperature interactions to make the metals more toxic. You'll also notice for the biocides like chlorine, about 40%, and so you can run right through these different classes. For some of the pesticides we see here, these would be the organochlorine pesticides here, the pyrethroids, and the carbamates, as well as the organophosphates. We see anywhere from 5 to over 45% of the studies showing adverse effects. And then we've broken down the individual trace metals, and I will point out for those very metals we see enriched in retention ponds in South Carolina: cadmium, chromium, copper, and zinc. I don't think they have, and lead. We see for 4 of the 5, we see almost all the studies are showing, for some of these metals, only adverse effects of temperature salinity interactions. Then finally, they have broken this down by phyla to see where the greatest effects are. And again, you see it in the phytoplankton, the bacteria, the annelid worms, your mollusk, and your crustaceans. Excuse me. So here's sort of a summary out of their paper of things that you might expect to see. In terms of mortality, drier summers will increase the death rate among animals. Temperature extremes will do that same thing. The higher ultraviolet light levels will increase bacterial death. Flooding in anaerobic conditions will also increase death in certain organisms. Increased temperature will increase growth. We're uncertain about some of the molecular aspects of how climate change will affect genes. So that the jury is still out on that. In terms of some of the chemical interactions, we know that photolysis will increase, so photodegradation, biodegradation will increase under climate conditions. We also see volatilization of chemicals will change, so you'll have greater volatilization, which means you're going to be transporting more in the atmosphere. We see increasing climate change conditions of temperature will increase bioconcentration, decrease bioconcentration with changes in salinity. So this is a very interesting paper. If you haven't read it, there's a lot of useful information. So I'm going to go ahead and sort of summarize what I've talked about today. And I hope what I've been able to show you today is that global change will cause alterations in temperature, salinity, or temperature rather, precipitation, and sea level rise that will alter estuarine water quality conditions, things like temperature, salinity, pH, dissolved oxygen. These climate interactions will also alter the ecotoxicology of many chemical contaminants in the environment. The increased temperatures in the Arctic will melt global ice and release these sequestered chemicals in that ice into Arctic ecosystems, which could have very dramatic effect. For example, those 2 pesticides we talked about will be most damaging to zooplankton and crustaceans. And we've all heard about the demise of many of the species of zooplankton, particularly that are ice associated, and most of those changes have been attributed to loss of habitat, but now we're factoring in another factor that makes a difficult life with loss of habitat even more difficult with exposure to chemicals that may cause toxicity. The lab studies indicate that these pesticides that we see melting in global ice may lower the thermal tolerances of freshwater fish, and of course this has major ramifications for future climate survivability as temperatures go up. Future climate change scenarios are predicted to increase the intensity of precipitation during rain events. This may lower salinity and reduce dissolved oxygen levels, particularly in urban areas with high rates of imperviousness, and we showed you some of that with the hydrolab data that we presented. The pesticide impacts to aquatic life are highest in urban areas already, and that's because of this imperviousness. Urbanization associated with imperviousness will cause even greater variability in water quality in addition to the changes that we see from climate change. So we make extreme become extreme in terms of changes in salinity, pH, and DO. Lab studies which have attempted to model this in the lab under controlled conditions show that these pesticides may be 4 to 5 times more toxic under extreme water quality conditions, which means our current regulatory testing for these chemicals has to be changed in order to better predict under future climate conditions. I want to finally close with a FITHRA Scientific Advisory Panel report I was part of with Dr. Peterson, Alistair Boxall of the UK, very prominent in climate change research in the European Union. And one of the things we stated in that report, in coastal areas where sea level rise is expected, our current pesticide exposure models are based upon soil saturation conditions of 40 to 50% soil saturation. With sea level rise, we may raise those levels to 80 to 90, even 100% soil saturation. And what that means is we will have even higher levels of pesticides expected to be discharged off an agricultural field or a site where those chemicals are used. So not only are we not estimating how toxic these chemicals are, but the estimated concentration we expect to see in the environment, we're also not factoring in climate change effects in coastal areas, which will make even more of the pesticide available. Again, I'm going to go to my colleague Ann Blair at HML and just show why this is so profound. You'll see under average rain runoff conditions using exam PRISM models that EPA uses, only about 40, and this is with a 55% impervious cover, you would expect only 42% of the rain to run off. However, you'll notice that if we have 100% soil saturation, you expect now 68% of the rain to run off because there's nowhere for the water to infiltrate. And because of that, that is over a 60% increase in additional loading, which will mean even higher pesticide or other chemical contaminant concentrations in the environment. And we have predicated the safety of these compounds under much lower soil saturation conditions with conventional toxicity tests that do not predict the worst extreme conditions under climate change. So I'm going to leave you with some important references that I have used in this presentation in case you want to get those citations, and I'll be glad to take any questions. Thank you.
Jeff, thank you so much for that excellent presentation. When I introduced you, I said that your research experience was vast. I think that was an understatement. So again, I'm going to open for questions, and we do have one question from Robin O'Malley. She says, or he says, I'm not sure, that besides showing increased concentrations of bad stuff with increasing population density and impervious cover are clear, but there are also significant pressures, including municipal infrastructure cost and energy use being the main ones, that argue for higher density. Millennial preferences may also push for new cities, an example being Tyson's. how do we reconcile these? Can we develop effective permeability metrics that we can use with higher density development to encourage or even measure reduced impact?
Well, the problem. Okay, let me just answer. The problem is we built laterally and not up. We tend to sprawl in most urban areas. At least that's been the historical pattern, rather than building up. And obviously, if you build up, you can accommodate more people in a smaller area with less overall imperviousness throughout a larger area, concentrating in it to a smaller area. So I think that's one way. That also gets to your issue of services for infrastructure and things like that. The problem is, we have not done a good job in the zoning laws that we have to really control development. For example, if you go out to Oregon, one of the best examples I've seen is putting an urban boundary and not allowing development to go beyond that. And what they showed with that is when you do that, you will then begin to build the infrastructure from mass transit and other infrastructure needs that we currently do not have, which today we're more reliant with sprawl of individual vehicles as opposed to having mass transportation. Then what follows are the food industry and other services people want, and that in turn makes building up and concentrating being more palatable to larger people. And when they've done that out in Oregon, I think this was in Portland, they have really prevented growth beyond the urban boundary. And instead what they have seen is development within that boundary. So if you look at the overall ecology of that region, they haven't increased the amount of imperviousness other than where they set that boundary. And so I think that's a good thing, as opposed to building beyond that boundary and having a larger effect. That's the best answer I can give you on that. It is a dilemma. It is something we have to start educating people about. And I do think the concern about infrastructure damage after this recent flood, we saw a classic example here in Columbia. Where do you put your entry point for your water intake system? Well, in Columbia, you put it in the lowest part of the river. Unfortunately, if a flood comes along, that's probably not the best place to have it. And you saw what happened in blowing out the canal. So on the other hand, if you have a drought, you're not going to have any water if you're not in the lowest part of the river. So, how do you, the issues get a little complicated.
All right. Okay. Robin, thanks you for that answer. She says it's very helpful. Thank you. We've got two more questions for you, Jeff. Lisa Wycliffe wants to know, how does climate change increase runoff of pesticides and ocean acidification influence future siting for inshore and offshore agriculture?
Well, I clearly think, obviously we've shown how toxic these chemicals can be, and clearly I think we want to, we have to feed ourselves. We use food as a commerce that we export. On the other hand, we also want to produce our own seafood because we currently import way too much of it. So I think what we have to be sure of is to put these in the aquaculture operations in areas, if they're onshore, we need to be very vigilant about monitoring around those areas to be sure that we are not seeing impacts on hatcheries and things like that. I know up in Virginia, where we had a lot of vegetable farming close to hatcheries, working with folks up there, we had a number of issues with runoff from vegetable farming there that damaged hatcheries, and once we were able to control that runoff, we were able to do that. And we did that through a combination of doing some great things that Lisa has been a real pioneer on, and that is you trying to get people to use safer pesticides, greener pesticides, less persistent, less toxic, moving away into more sustainable pesticide use. And Lisa has a great little website that she did as part of her dissertation research on this called the South Carolina Coastal Pesticide Decision-Making Tool, which gives people information on going green in terms of using safer pesticides. So clearly, I think that can help, because again, where are most people using pesticides? It's not the farms anymore; it's urban areas, and so we have to really be sure that we have information. In the site Lisa has information to guide people in selecting the less toxic options and the pesticides that are safe to use. For example, if they're in a flood area, flood code, where it's going to frequently flood, the label says do not use near water. You shouldn't be using that pesticide. It'll tell you that. So we have a nice way to enforce the label by, providing information to consumers so they understand that.
Okay, thank you, Jeff. She says that's a great answer. And we've got maybe 30 seconds for you to answer this question for Jen Bennett. She says that it looks like low O2 concentration rather than low pH shifted the LD50 of the organisms you studied. And do you have any insight or know of any research getting at why that might be the case?
Well, I think the issue is, and I think you were very astute in looking at that, Jen, we saw a slight drop. Remember, the pHs we were testing, that the NOAA folks were testing, were only at 7. And what would be good would be to go lower with that pH. The final thing I'll say is, one of the things I think you saw from the Hydra labs is you're going to get both low pH and dissolved oxygen co-occurring. You're probably almost always going to see those concomitant conditions. So we really need to be testing those combinations. But this is clearly an area of research we need to do more on.
Okay, great. Thank you, Jeff. So if we didn't get to your questions, or you have questions that you think of later about today's presentation, please feel free to contact Jeff via...
And I just put my contact information on the screen there for you.
Okay, great. Perfect. Thank you. So you can contact Jeff via the contact information there. And if you are interested in joining the SOCAN listserv to learn more about the network or future updates, please sign up at the URL that you see here at the site on this slide. And please direct any questions about SOCAN to socan@socorro.org. Thank you for attending this webinar series today. We welcome any feedback on the webinar series, and you can submit that by replying to the follow-up email that you will be receiving from us shortly. As I mentioned earlier, a recording of this webinar and a PDF of this presentation will be available on the SOCAN website. Jeff, thank you again for the excellent presentation. And our next State of the Science discussion will be in 2 weeks on Tuesday, December the 7th at 12 o'clock noon. More information about that presentation and how to register will be available on the SOCAN webinar series website shortly. We hope that you'll join us. We wish you all a happy and a very safe Thanksgiving holiday. We hope to see you again soon in the